Welcome to week two of the RCP program, year one, week two. So you've decided to come back, got through your first week, and you're still ready to get after it in the second week. So that's good. Last week you had an intro to respiratory therapy. You probably learned about the AARC, the MBRC, COARC, the Commission on Accreditation for Respiratory Care, which is the accrediting agency for your entry-level practice programs, with baccalaureate programs if they happen to offer higher degrees in respiratory therapy as well. This week, you probably learning a little bit more about the profession, the overall roles of the respiratory therapist. You've probably been learning hearing some terms such as evidence-based medicine. So those are some things that we'll continue to talk about. I know you'll continue with principles of infection control and infection prevention as well. Uh, Moving forward. So we have our introductory class, our pharmacology class. We also have our clinical class. I know in clinical, you're going to begin to talk about oxygen therapy a little bit um, this week. So that's going to kind of be the overall brunt of what, and I'm going to try to keep this relatively short, hopefully not much longer than 5 minutes uh, uh, if I can keep it that short. But nonetheless, to achieve that feat, I'm going to kindly be quiet about the introductory stuff from last week and this week, and we'll go ahead and move forward with our presentation uh, as we get underway. So you're going to begin oxygen therapy, uh, and we utilize portable oxygen systems. Most hospitals are going to have bulk oxygen systems. You'll learn more about that and can read more about that. But I wanted to go over some of the calculations that will deal with some of the portable oxygen systems. So if you've known anybody that wore oxygen at home, whether they're using an oxygen concentrator or they've got a cylinder bank, you've likely seen someone with uh, probably some of these smaller cylinders that you would see over here. But nonetheless, the two cylinders that we're going to kind of focus on are three, if you will, one not pictured. With H and K are roughly about the same size cylinder. So you can see me moving my cursor over the H or K cylinder. It probably stands. I don't have the exact height dimensions. However, I'm 5'10" and I'm taller than that cylinder if I go stand beside of it. If you want to see the H and K cylinder, go to our laboratory room, in the manifold room where the four cylinder bank is set up, and you'll be able to see the approximate size of that. And you've got several E cylinders in our labs, and those are what you're going to learn with your O2 transport, placing nasocant or providing supplemental oxygen via nasopharyngeal to an individual. So these are the two primary cylinders, the E cylinder and the H or K cylinder, that we're going to focus with. But I do want you to understand that for home care environments and so forth, you may see any combination of the other cylinders. These become a little bit less cumbersome. However, they obviously are going to have less volume. You're going to learn about your gas laws and so forth moving forward, volume and pressure and the relationships with those. But nonetheless, those are the couple of cylinders that we're going to be working with this week. So you're going to be asked to calculate oxygen cylinder duration. Absolutely got to be able to do this. It makes sense to be able to know how to calculate how much oxygen is in a cylinder and how long it's going to last, because you may be asked to go on a transport with a patient that's going for a procedure, what have you. You should have the luxury of, just for the transport, using the oxygen cylinder. And then once you get where you're going, hook up to a wall outlet. You'll learn about the safety systems associated with that too. Briefly, I'll mention those. You've got the American Standard Safety System, diameter index safety system, and the pin index safety system. The pin index safety system is going to be utilized on E cylinders and smaller. American Standard Safety System is going to be utilized on those larger cylinders, such as the H or K cylinder that we talked about. And the diameter index safety system, when you guys are hooking your flow meters and stuff up to the wall, that's the safety system associated with that. Ultimately, the pin index safety system, diameter index safety system, American Standard Safety System, they're all put together so that you are, when you're placing your regulators and so forth, or your flow meters on these cylinders, that you're only able to put an oxygen cylinder to an oxygen regulator or oxygen flow meter to an oxygen cylinder, and vice versa, because there are different gases that are available in medicine. Two of the primary gases we'll work with is medical grade oxygen, medical grade air. We'll go over the color schemes and stuff of that a little bit later on, but the universal green is for medical grade oxygen, yellow is for medical grade air. As far as calculating the time, and again, I'm starting to get over verbose, so I want to keep this try to as succinct as possible. So we'll stick with this. So we've got to know the oxygen cylinder factors. Let me see if I can get this so that I can write on the screen quickly. And I'll probably use white as a background. That may show up best. But nonetheless, you absolutely have to know your cylinder factors. And we do have the E cylinder and we have the H or K cylinder. And I will forewarn you, I never got significant remarks on my penmanship other than it's not very good. Uh, but you know, it is what we have. I've not figured out a way to speed up the typing so that I can get everything in. So it's easier just to put my chicken scratch on the screen. So your cylinder factor for an E cylinder is 0.28. You need to go ahead and commit that to memory. H or K, and that's as easy as pie. It really is true because the H or K cylinder, their cylinder factor is the same, and it's 3.14. And if you remember pi from way back when in school, 3.14 is there. So if you remember pi for H or K and 0.28 for your E cylinder. So you also got to know the formula. The formula for calculating cylinder duration is cylinder pressure times cylinder factor divided by your flow. So ultimately, you're going to have you'll have a patient that's receiving supplemental oxygen, maybe via nasal cannula at 3 liters per minute. That's going to be your flow. Cylinder pressure, you'll look at a pressure gauge on that cylinder and you'll be able to determine how much pressure is inside of that cylinder just by reading the gauge. So it's going to be important for you to understand how to do that. Typically, there's going to be 2 different units of measurements, whether that's PSI or KPL, kilopascals. We're going to do everything in PSI. You may also see a PSIG, pound per square inch gauge. With that being said, make sure that you can read those gauges. You get down and read them at eye level because that's going to be an important factor being able to determine how long the treat is going to last. And then you have your cylinder factors committed to memory. We'll have some practice on the next slide with both an E cylinder and an H or K cylinder. So remember 0.28 as the E cylinder factor, 3.14 or pi for your H or K cylinder. And the overall formula is cylinder pressure times your cylinder factor divided by flow, and flow for us is going to be measured in liters per minute. There are instances where we'll look at liters per second, but that'll be some other things that we'll cover a little bit later on down the road. We are going to go liters per minute here. So once you do this calculation, your answer is going to be in minutes. So it'll be the total amount of minutes that that cylinder is going to last. You may be asked to report your answer in hours and minutes. So in order to do that, take the total number of minutes and divide that by 60 so that you can break that down into hours and minutes. So if you remember the old school way of doing so if I, 80 minutes and I divided that by 60, then I know 60 will go in there one time with a remainder of 20 minutes. So it's an hour and 20 minutes. But if you plug 80 divided by 60 into a calculator, 80 divided by 60 into a calculator, you're going to get 1 point. So the answer with 80 divided by 60 on the calculator, that equals 1.33 repeating. You're probably not going to report that as 1.33 hours. So what you would do, you take that 0.33 at that point, if you need to convert that to minutes, and multiply that by 60. And that ends up being 19.8 around up to 20 minutes. So 1 hour and 20 minutes is going to be the answer that you've got there. So let me clear this off of the screen and we'll go do a couple practice problems. All right, so 2 practice problems. I'll bring up my writing feature again. And you've got an H cylinder. So we know up here we are utilizing the 3.14 cylinder factor. That's what we're going to utilize because it's an H or K cylinder. Shows that the pressure is 1750 and the oxygen flow is set at 10 liters per minute. How long is that cylinder going to last until empty? So how long will that cylinder last until there's nothing else left in the cylinder? So remember the formula, you're going to take the cylinder pressure, multiply that by your cylinder factor, divide by flow. So our cylinder pressure is 1750. Multiply that by our cylinder factor of 3.14, and we will divide that by 10. it's 10 liters per minute. So 1750 PSI, 3.14 is a conversion factor, and then you've got 10 liters per minute underneath there. So, you know, and do everything on the top first. So I'll utilize my calculator, 1750 times 3.14, and that is 5,495. 5,495. Then we'll take that, divide that by 10, divide that by 10, and that is 549.5. That equals 549.5, and that's 549.5 minutes. Remember, I need to divide that by 60 and break that down into hours and minutes. So I'll take that, divide it by 60 on my calculator, and I get 9.1. It rounds up to 16 hours. But you need that in hours and minutes. So take that portion of that right there, 0.16, and multiply that by 60. So 6 times 60, and that gives me 9.6 minutes, or, you know, it's not a full 10. You could round up to 10 minutes, but we'll just leave it at 9 minutes. I know that's 9 whole minutes. So I've got 9 hours and 9 minutes. But that's going to run 9 hours and 9 minutes. That this cylinder will last. That, and the HOK cylinder is much larger than the E cylinder. So you'll notice the next practice problem that we have is for an E cylinder. So that gauge shows that it's 1400 psi. They're receiving supplemental oxygen via 2 liters per minute nasal cannula. The patient is traveling to the beach, and they live 5 hours from the beach. Assuming there are no traffic issues, arrival is going to occur within 5 hours, and there's no need to increase the oxygen flow along the way. Will that E cylinder be long enough for that patient to make the trip? Hopefully they'll have an oxygen concentrator where they get where they're going. But we will understand is one cylinder at 1400 psi running at 2 liters per minute going to be long enough for this individual to make that 5-hour trip from where they live to the beach. So again, same formula. You're going to take 1400. Multiply it by your cylinder factor. It's different now. We're using an E cylinder. It's going to be 0.28, and we will still divide everything by our flow, which is going to be in liters per minute, and this is 2. So we take 1400, multiply that by 0.28. That is 392. 392. Then we'll divide that by 2. Is 196 minutes. 196 minutes. Divide that by 60. This is 3.27. 3.27 minutes. You can move forward at this point with figuring out exactly how many hours, but you know it's 3 hours and 0.27 minutes, 3 hours and 0.27 minutes. So 0.27 times 60 gives us 16 minutes. So 3 hours and 16 minutes essentially. 3 hours, 16 minutes. The question is, will that one cylinder last them long enough? If it's a 5-hour trip and I have one cylinder, 3 hours and 16 minutes into that trip, they're going to run out of oxygen. So they'll need to take an additional oxygen cylinder with them. And those cylinders are pretty full at full, they're roughly 2200 psi. But that can change, and you'll learn about the stamps and the service pressure and stuff like that on the cylinder in class, and we can talk about those, review those forward. But I know I'm over the 5-minute time limit. There's still a couple of things that I want to get, so maybe we'll be less than 10. Clear that drawer and we'll move forward. And then lastly, I know in the pharmacology class you went over drug dosage calculation, the metric system. Got to understand the metric system. Everything we're going to do in medicine and a lot of what you're going to do in respiratory therapy is going to entail and involve the metric system. And it's liters per minute and so forth that we just talking about. That's a base unit. We didn't have to convert too much in there, but if you're going liters per minute to liters per second, you know, that's not going to be a metric conversion per se, but still converting. Uh, so you know that in the metric system, you have your base units, that's liter, meter, and gram. You know that if you move to the right, I mean this KHDBDCM up here. If you remember the mnemonic device, King Henry died by drinking chocolate milk. B represents your basic unit. So if you move to the right, you're going to a smaller unit. If you move to the left, you're going to a larger unit. We'll typically probably focus on liters and grams, whether that be milligrams, milliliters, or what have you, moving through there. But nonetheless, you need to know how to move to the right or left, how to move your decimal. And you can do that simply by moving the decimal, or you can multiply by the tens places, hundred places, thousands places, however you prefer to do that. A practical application of this is going to be in a dose calculation. So for instance, you had a patient that is to receive a 0.02% solution of atropine or ipratropium bromide. And you also learn that that's a bronchodilator. It's an anticholinergic bronchodilator, but that's for a different discussion. We'll stick with the math right here. How many milligrams of active ingredient are in a 3 milliliters of solution? So when you have a 0.02% solution, we'll read that. Let me turn my pen on real quick. We'll always read that as 0.02 grams over 100 milliliters. And we're asked how many milligrams are in 3 milliliters of solution. We'll keep the volume in the denominator, we'll keep the weight of the medication in the numerator. So ultimately you'll cross multiply, but it's easier to cross multiply if you go ahead and have right numerators and right denominators. The denominators are already right, so this is where the conversion is going to come up with. So our answer ultimately is going to be in milligrams. So I think it would be easier on the front end to convert 0.02 grams to 0.2 milligrams. So if you go up here to your base unit and you have 0.02 grams. We start at grams and we know that we're wanting to go to milligrams. So we're going to go 1, 2, 3. You'll move the decimal spot to the right three places. So we're going to go 1, 2, 3. Decimal goes there, fill that dividend with a 0, and ultimately you're looking at 20 milligrams. So now we can plug that in. We can plug that into our formula down there. So we'll rewrite the formula as follows. 20 milligrams over 100 milliliters equals X milligrams over 3 milliliters. Now all you've got to do is cross multiply. So 100 times X. So we go here and here. 100 times X ends up being 100X. Set that equal to the next cross multiplication. So 20 milligrams times 3 is 60. Now you've got to get X by itself and divide both sides by 100. X equals 600. That's about 60. Well, 0.6. So that gives you your answer in milligrams. So the answer to that question is 0.6 milligrams. You'll have plenty more practice during class, but I wanted to provide an overview and a practice example of that. We are out of time for this week, but this was a quick overview of your week 2 and some of the content that we had talked. I'll try to do something beginning week 3. Thank you all for your time and attention. I hope you have a good day.